Hello and welcome to yet another webinar in this series of MI2. MI2 webinars are focused on the convergence of machine intelligence and modern infrastructure. Machine intelligence is all about IoT plus AI, while modern infrastructure is all about containers, microservices, and managing them. Every other week, I bring you a session focused on one of these tracks. And today, I'm very excited to bring you Istio. The calendar for the entire quarter is published at mi2.live. I encourage you to go ahead and sign up for the upcoming sessions. My name is Janakiram and I'm going to be the presenter for today's session. Since this is all about Istio, I want to set the context about service mesh. So I'm going to talk to you about what are the motivations for using service mesh in your projects, and then we'll take a closer look at Istio, followed by a very comprehensive demo walkthrough. Like each of my webinars, this session is also accompanied by source code and a tutorial. If you're watching this on YouTube, click on the more link in the description to find the link to the slides, to the tutorial and the source code. So let's get started. I'm not going to cover the differences between monolithic and microservices architecture, but assuming you have already embraced microservices, there are quite a few challenges. Microservices are based on polyglot development, which means you're going to handpick best of the breed languages, tools, and frameworks. And this makes it difficult because every service is written in a new language. So there is no consistent set of tools or frameworks or libraries that you could use across your microservices project. They're highly distributed. If you are running microservices in a cluster, there is no guarantee that a service is going to be deployed only in one of the physical hosts or virtual hosts. They are extremely distributed, which makes it very difficult to debug because there are multiple services and multiple instances of each service. When something goes wrong, it is very difficult for you to find out what went wrong. So debugging becomes extremely challenging. Same is the case with monitoring, logging, and tracing, because you have to centralize, aggregate, collect, and then make sense of the logs and the monitoring data coming from this distributed infrastructure plus application environment. Services dynamically scale in and scale out. You never know how many instances of your services might run at any given point of time. Thanks to concepts like horizontal and vertical pod auto scaling in Kubernetes, microservices are going to be scaled out and scaled in without any intervention. And this makes the DevOps job or even the developer's job very hard, particularly when it comes to debugging, finding the root cause, and getting the state of your application. Microservices use a variety of protocols, and that is again a big challenge because you cannot standardize on just REST or gRPC or NATS or GraphQL, for example. And microservices implement both internal and external load balancers. External load balancers for driving the north-south traffic from the outbound traffic towards your service environment. Internal traffic or internal load balancers are used to load balance the traffic within multiple instances of your microservices. So you have to deal with a variety of load balancing techniques across the deployment. So this is a visual representation of the challenges involved with microservices. So the way you can address some of this is to write an agent, and this agent is specific to the language that you have chosen for your microservice. For example, a microservice written in Python will have to have an agent written in Python, and same is the case with rest of the microservices. Now, all these agents are like SDKs that are very specific to the language and also very specific to the application that you are writing. Sometimes it may be hard for you to generalize, and the job of the agent is to intercept the traffic and making sure that the outbound call is indeed going to the respective service, and if the service is failing multiple times, it knows where to break the circuit and raise an exception. So these agents are going to be the close companions of every service, and they will report the current state and the health to a central monitoring service. Now you as a developer is responsible for writing these agents and also to ensure that they are highly available, and then there is a control plane that is monitoring all these services that are distributed, and you need to write that monitoring service and also maintain it. And this makes it very, very expensive because you are going to invest in multiple agents that are specific to every language, and then another layer that is responsible for managing all these agents. So you will have to invest in maintaining pretty complex projects that are outside of the scope of your core line of business project, and this makes it cumbersome, expensive, and very, very tough to maintain over a period of time. So that's where service mesh comes in. So service mesh plugs itself into the intra-service communication layer. So if you visualize an environment where you have multiple services, let's call them service A, B, and C. So the service mesh puts itself right into the call between service A and service B. So every outbound call from service A and every inbound call from service B is going to be intercepted by the service mesh. In most of the cases, service mesh is used for east-west traffic, that is the horizontal data plane that is used for sending messages and used for intra-service communication. But in some cases, when when service mesh is associated with an ingress or a load balancer, it is also quite capable of managing north-south traffic, which is an inbound traffic coming from the outside world like public internet. The service mesh, because it sits very close to the microservice, can capture telemetry and a lot of insights on the service health and the traffic patterns. And it calls home, which is the control plane, to submit the telemetry and aggregate the telemetry coming from the distributed deployment of your microservices. It also brings in implicit security, because when microservices are calling each other, the developer need not implement security explicitly. Service mesh can implement an MTLS layer by bringing in authentication, authorization, and policy-based call chain. And all of that is declarative, so that your code is completely agnostic to the security layer. It also enables service discovery by bringing in a homogeneous way of talking to an endpoint, and that endpoint can indeed talk to multiple versions or multiple revisions of your actual microservice. So if you have multiple versions, let's say V1, V2, and V3, all of them can be registered with one service endpoint, and at runtime you can define how the traffic is going to be routed to one of the versions. And that brings us to policy-driven routing and traffic management, which is a very powerful feature of a service mesh. Service mesh is not just meant for microservices. It can also integrate with virtual machines and even physical hosts. And this brings in a pretty interesting scenario of hybrid of both VMs and containers, hybrid of both on-prem and cloud. Of late, a lot of vendors have been investing in service mesh and making their hybrid cloud stack based on service mesh. The most recent announcements from Google, like GKE on-prem, Anthos, Traffic Manager, and so on, are built on top of a service mesh. So it is not just confined to microservices. Excellent. So we have just discussed, but to kind of answer some of the questions that were raised right at the beginning, why service mesh? So service mesh delivers an out-of-proc architecture. Your code is not at all aware of the service mesh layer. It just works because it's a plug-in replacement for your DIY agents and brings in pretty good separation between data plane and control plane. So you can focus on your business logic while the service mesh is going to take care of the data plane, that is the traffic flowing across your microservices, and the control plane responsible for managing the data plane. Supports both internal and external load balancing across L3, L4, and L7 layers. So you don't need to explicitly implement a load balancer, whether it is internal or external. As I mentioned, service mesh can latch on to the ingress and the load balancer and delivers external traffic conditioning and policies, as well as internal. Consistent service discovery, as I mentioned, you don't need to worry about routing the traffic to one endpoint and from there to a respective version. So all of that is done seamlessly and very transparently. Extensible protocol support. Service mesh can integrate with most popular protocols, all the way from HTTP to HTTP2, gRPC, NATs, and even external stateful services like DynamoDB or MongoDB or Cassandra. So service mesh can understand all of these protocols and can implement intelligent routing and intelligent telemetry. Service mesh brings in advanced health checks, which means you can implement interesting capabilities like circuit breaking, where if a service is repeatedly failing, the callee will stop calling that service because it is constantly generating errors. So that saves bandwidth and very expensive round trip across your network, and also gives you a very proactive way to monitor and manage failures and errors. So it brings in resiliency. And because the service mesh agents, the data plane sits very close to the microservices, it can provide real-time observability by streaming, monitoring, logging, and tracing information to the centralized control plane, and delivers highly powerful, insightful visualizations and dashboards. And finally, service mesh implements best practices of distributed computing. So this is how we can visualize the service mesh. The earlier diagram that I have shown you was DIY. You had to write the agent, you had to write the monitoring service. With service mesh, it comes in out of the box. You just need to inject a sidecar as a proxy into every service, and then the service mesh typically comes with a control plane that is already resilient, and you can just ensure that it is highly available. So you don't own the purple blocks in this diagram. You only focus on your services, while the service mesh takes care of the data plane and the control plane. So what is Istio? Well, everything that I described and attributed to service mesh is 100% applicable to Istio. So at a high level, Istio does 4 things. Number 1, it connects via intelligent traffic routing and flow. It secures microservices communication by managing authentication and encryption. It controls the traffic through policy-driven communication across services. And finally, it does deliver great observability by automating tracing, monitoring, and logging. So Istio is the service mesh that basically comes with the data plane and the control plane. And if you look at the way it is organized now, mapping the concept of a service mesh architecture to Istio. So there is an Istio control plane, and then there is an Istio data plane. So let's start from the data plane. So the data plane is composed of a proxy, which is a sidecar that is sitting next to your service. And that proxy is based on Envoy. So Envoy is an open source proxy developed at Lyft, and it is very, very powerful, very extensible. And Istio leverages Envoy as the proxy. So Envoy injects itself into every microservice, and this proxy is responsible for pulling the policies submitted to Istio control plane and pushing the telemetry from each of the services back to the control plane. Because there are multiple instances of proxy and you don't want to deal with one at a time, you would use the control plane as the centralized entry point for pushing all the policies. And the control plane is also responsible for collecting, aggregating, and showing the visualizations of monitoring, tracing, and debugging information. So the other dimension of looking at Istio is this. So you have multiple instances of microservices, and every instance has a proxy. Proxy calls home, which is the control plane, and control plane is responsible for observability based on telemetry, network management based on policies, service discovery based on a very consistent scheme. So the policy definitions are submitted to the control plane, and that flows down to every proxy, which is the Envoy instance running within the microservice. Taking a closer look at the architecture, so you have the control plane that is composed of multiple components. First of all, there is Mixer, then there is Pilot, then there is Galley and Citadel. So the Mixer is going to be the endpoint to which all the proxies will talk to. So the telemetry would flow into the control plane via the Mixer. And the Mixer is also responsible for using a plugin architecture where it can stream the telemetry to a variety of environments. For example, Datadog, Stackdriver, CloudWatch, or Elk Stack. It depends on how you want to extract the logs and monitoring information and visualize. So that has the adopter architecture where you can easily plug and play with multiple industry standard monitoring and logging tools. Let's understand each of these components a bit better. So there is Pilot, and Pilot is responsible to configure and push service communication policies. So Envoy understands the policies in a specific format, in a specific protocol, and that may not be the best way to deal with your overall policy enforcement. So Istio exposes a more comprehensible, easy to understand and easy to use policy definition. But when you submit it to the control plane via the API, it's the job of the pilot to translate that schema, that protocol, and that format to a language that is understood by Envoy proxy. So that is the job of pilot. Translate everything and push it to every proxy. Envoy, it's a network proxy that intercepts the communication and is responsible for enforcing the policies. It attaches itself to every service and constantly talks to the control plane to make sure that it is pushing the most recent policy and is also sending the up-to-date telemetry. Mixer is a policy enforcement with a flexible plugin model. So a mixer is the core component that all the proxy components will report into. So Envoy talks to Mixer, and Mixer is responsible for enforcing the policies coming via the pilot. And it is also responsible for ingesting the telemetry into third-party environments through the plugin adopter model. Citadel is responsible for implementing security and mutual TLS. So it comes with built-in identity and credential management. So you can implement a very fine-grained role-based access control and service-to-service communication policy through Citadel. Galley is responsible for interfacing with the orchestration engine. For example, when you're running this in the context of Kubernetes, it is going to interface with Kubernetes. For example, how it translates the inbound calls from the ingress controller and how it implements Kubernetes specific policies, how it integrates with the RBAC and rest of the secrets and so on. So all of that is responsible is responsibility of Galley. So it is closely working with the underlying orchestration engine, which could be Kubernetes or Mesosphere or Nomad or any of the popular supported orchestration engines. So when it comes to traffic management, and because this session is of 45 minutes and I cannot obviously cover everything, I'm trying my best to bring you all the core capabilities and provide you an end-to-end demo. So let's focus on two aspects of Istio. One is traffic management, the other one is telemetry. So first, let's look at traffic management. So visualize an environment where you have the Kubernetes ingress and Istio attaches itself to that ingress, and let's call it as the ingress gateway. So the ingress gateway is responsible for getting the traffic from Kubernetes into the Istio context, into the Istio environment. So that is the gateway. It is the load balancer and responsible for routing the HTTP and TCP traffic from the edge into the mesh. And mesh is a collection of microservices with the Envoy proxy injected into it. So gateway will drive the traffic into the Istio service mesh. And Istio service mesh could be implemented within multiple namespaces, multiple projects. Now the traffic has to be routed to an appropriate service. For example, in a multi-tenant environment, you might be running multiple instances of the same application, but running in strong isolation. Could be namespaces, could be network policies, could be even clusters, separate clusters. So how do you take that traffic and route it to the appropriate deployment? And that's where virtual service will come in. So virtual service defines the rules that control how an inbound traffic hitting the edge at the gateway level finds its way to the appropriate service. So that is the virtual service, which is the link, the conduit, the channel between the ingress gateway and the actual service deployment. And once the traffic crosses the virtual service, it basically gets into the destination rule, and destination rule is responsible for driving the traffic to an appropriate service endpoint. So for example, you might hit product page, and product page might now needs to talk to let's say multiple versions, and that version is responsible for ultimately getting the connection and getting the traffic, the request. So it's a multi-layered approach. The traffic comes all the way to the gateway, and from there it comes to virtual service, which is the edge of Istio, the second layer. And the third layer is actually the service itself that you have implemented, and this could be your Kubernetes cluster IP. So that is the destination rule, and that's how you wire up this request all the way to one of the services that you have deployed in Kubernetes. All outbound communication goes via the service entry. If service A is talking to service B and service B is the backend for service A, the service entry is responsible for resolving service B within service A, and that is the service entry. It is basically meant for outbound traffic that is going even outside of the context of Istio. And finally, sidecar is the envoy proxy that is sitting next to every service, and that is how the network topology is laid out. In terms of telemetry, we have metrics, logging, tracing, and all of that is rolled up into fantastic visualization, very powerful, and I'm going to show you a demo of this. So what are we going to deploy? Well, the promise of MI2 webinars is consistent repeatability. So the objective is everything that I show you here, you should be able to do it in your own environment. So every session is accompanied by a video, the slides that I am presenting, sometimes the concept and the background, the tutorial, which is a step-by-step guide, and a pointer to source code. So right after this session, I'm going to send out these links to all of you, and they're also put up in the YouTube video. Just click on the more button and you can see the links to all of the resources I mentioned. So you can replicate exactly the same scenario. Now coming back to the use case that we are targeting today, because I want this to be repeatable and consistent, I'm actually going to base this demo on book info sample, which ships out of the box with Istio. So when you install Istio, the book info sample is a part of that. And what does the book info sample do? So book info has 3 microservices. The first microservice is the front end, which is the product page. This is written in Python and Flask, and it basically shows the user interface. And this microservice talks to reviews, and reviews has multiple versions. The first version of reviews only has text that is coming as an output. The second version of reviews sends a set of black stars, which is like a 5-star rating on a scale of 1 to 5. And the version 3 of reviews sends the 5-star rating in red stars. There is also a microservice written in Ruby, and that is going to send the details of books. And finally, there is a rating service which is written in Node.js, and maybe that talks to MongoDB, and that's how the ratings are pulled from the data store and translated into a set of stars. So this is the hierarchy. So you have the product page calling reviews, and reviews calls ratings. Product also calls details. So we're going to see how to install Istio, and then configuring the traffic rules and visualizing telemetry. So let's get started. I'm going to base this demo on Minikube. So when you are actually doing this with Minikube, make sure you allocate enough resources. I had issues when I didn't give it enough memory and CPU cores. So it's always recommended that you assign 8 GB of RAM, at least 4 cores of CPU, and then launch your Minikube single node cluster. You could also use GKE or any other managed Kubernetes infrastructure. So let me show you my environment. So this is my Kubernetes environment. It's running on Minikube. It's up and running for the last 6 hours. and it is launched with the same configuration. Now, once we have Minikube or access to Kubernetes cluster, it's time for us to deploy Istio. So this command that you see is a helper script that grabs the most recent version of Istio and gets that into your local dev machine. So I have already done that, and that's the reason why you see that I am already in this directory called Istio 1.1.3. So that is the most current version as of this session. So that's the outcome from this command. Now, if you are using Istio on Minikube and you are using the typical Kubernetes way of installing Istio and not the Helm chart, you can actually modify the Istio demo.yaml, because this is going to focus on exposing the ingress as a load balancer, and we have to change this to node port. So on line 15489, you got to change load balancer to node port. If you're using a Helm chart, then you don't need to do this, but if you're deploying it the way I'm showing, you got to modify load balancer to node port so that you don't have issues accessing the ingress gateway. And you can leave this as is if you are using a public cloud based environment like GKE or EKS. So I have already done that. Now it's time for us to go ahead and deploy Istio. So I'm going to grab this line, which is going to install a bunch of CRDs. A CRD is a custom resource definition in Kubernetes. So this integrates Istio very tightly with Kubernetes so that you could use one CLI, which is kubectl, to manage not just Kubernetes but also Istio. So let's go ahead and run this. Meanwhile, I'm going to put something in a watch mode. So the outcome from this command is going to put a lot of pods and services inside a namespace called Istio system. So let's actually start watching this. So when it is in watch mode, I'll go ahead and deploy the CRDs first. And once the CRDs are deployed, we are going to launch the pods and services. And the pods and services have a dependency on CRDs. So make sure the CRDs are rolled out first before you install the pods and services. So all we got to do is kubectl apply Istio demo.yaml within install Kubernetes directory. And this is going to be responsible for creating the pods and services. And it immediately creates a bunch of pods and deployments and services within the Istio system namespace. So this is going to take a minute or two, depending on your bandwidth and the resources you have assigned to Minikube or your cluster. But looks like this is moving fast. In about a minute, we should actually have everything up and running. I have also launched the dashboard. So here, if you actually look at the dashboard, you can see there is Istio system, and within Istio system, we can go to pods, and most of them are up and running. The orange color exclamatory sign that you see, the alert, is basically for those. There we go. So now Istio is completely deployed and is ready. There are about 15 pods, and obviously it comes with a bunch of deployments. These are all the deployments that translated to multiple pods and replica sets. It also comes with a set of services. So in the Istio system namespace, you also notice there are a lot of services. The most important one is the Istio Ingress Gateway, which is responsible for all the outbound traffic, the inbound traffic coming from the outside world. So this is going to be our endpoint for sending in traffic and accessing the microservices. So that was how we installed Istio. So very simple, 3 commands: grab the latest build, install the CRDs, and then go ahead and deploy Istio. And we looked at the number of pods. There are about 15 of them, and the number of services that are created as a part of this installation. Perfect. Now, with this in place, let me go ahead and launch the actual application. Now, the application that we're going to deploy, as I mentioned, is Bookinfo. It lives within the Istio samples directory, so we don't need to clone anything else. But before we do anything with the deployment, we got to configure auto injection. Now, what it really means by auto injection is automatically injecting an Envoy proxy into every pod that is deployed in that namespace. So you don't need to explicitly add the Envoy proxy. By default, every pod scheduled or placed inside this namespace will automatically have the Envoy proxy attached to it. And that is very handy to automate Envoy proxy injection in almost every pod that we're going to deploy in this namespace. So we'll go ahead and annotate this namespace called default. That is where we're going to deploy our bookinfo sample with this tag called Istio injection is equal to enabled. And this is an indicator to Istio that anything that goes into this namespace will automatically have the Envoy proxy attached to it. That's the first prerequisite. So currently we don't have any pods or any services in this namespace. It's a blank slate. And now we are going ahead and deploying the bookinfo sample. So let me launch this. So now let's actually put this in watch mode. So kubectl get pods will show us, let's spend a minute understanding this. So there is product page v1. This is responsible for the front end. Product page talks to reviews, and we have three versions of reviews, v1, v2, and v3. v1 textual reviews, v2 a black star, v3 is a red star. And reviews service talks to ratings. And product page also talks to another microservice called details. Now everything is up and running. We can also visualize this in the dashboard. So if you look at the default namespace, these are the microservices, these are the service endpoints, and these are the deployments. If you actually see, it all translates to the same topology and the architecture that I have discussed earlier. So we are now ready to access the sample application and see how it looks like. But before that, we need to do a couple of more things. So we need to wire up the traffic to the bookinfo product page. So the way we do that is to register the gateway that is responsible for routing the traffic to the product page. So this is how, for example, let me show you the code inside this. So this is where we actually accept the traffic from the ingress. So the traffic first comes to the ingress gateway, and this is not specific to bookinfo. Any traffic hitting our cluster will touch this endpoint, and from there we bring it down to a virtual service, and virtual service says the headers and the URIs, when they match any of this, send it to the product page, send it to the bookinfo sample. So this is how we wire up the traffic coming, the generic traffic coming via the ingress gateway to one of the services. So this is the gateway that we have just created, and it is responsible for routing the traffic into our microservices app deployment, which is the bookinfo sample. Then we also need to create a rule saying that this is now responsible for talking to either v1, v2, or v3. So a destination rule is registering all the versions of our microservices. And if you look at ratings, for example, reviews, we have three versions, v1, v2, and v3. So we are basically registering all the available versions as the microservice endpoint. So this is the destination rule. And if you look at the destination rule definition, that's exactly what you would see. So it says product page, it has only version 1. Reviews has 3 versions registered, v1, v2, and v3. And the ratings is registered as v1 and v2. v2 talks to MySQL, and v1 maybe talks to Mongo. So that's why it is kind of differentiated. And then there is details. Details also has v1 and v2. These are all high-level definitions saying, hey, every service has the listed number of versions. That's exactly what we do with a destination rule. Now, once we have the destination rule in place, we need to basically create the actual topology saying that, route the traffic to all v1. So this is the last step. And what this does is, based on the destination rule where we registered all the versions, it starts wiring up the actual components that have V1 across board. Product page, reviews, ratings, details, all the traffic will go to V1. So now our application is deployed and we are ready. So I can actually test the deployment from the command line. So what we actually do is we get the pod responsible for ratings, and ratings has access to product page. Because of the service discovery, we can use the service name, and we are doing a curl on the product page. And because it is spitting out a lot of HTML, we are only grepping the title tag. So if everything goes well, we should actually see some output. There we go. So now it actually says simple bookstore app. That means our application has been successfully deployed, and it also makes me feel very good and comfortable looking at all the pods in running mode with no restarts. Earlier I had mixed results, so this is a pretty good sign. Perfect. So now that we have the deployment ready and everything is up and running, let's go ahead and access the application. So what I'm going to do now is to grab the Minikube IP. So that's where the ingress lives. So I'm first going to grab the Minikube IP, and then we also need to get the port on which the ingress gateway is listening. So that is the port on which all the microservices will become accessible. But thanks to the concept of a virtual service, when we inject a header or a URI, it finds its way. Now we are finding the ingress port of the ingress gateway registered on Minikube. So let's take a look at this entire URI that we just constructed. So ingress host colon ingress port, and this is how it's going to look like. My Minikube lives on 192.168.9900, and the ingress is available on 31380. So that is the node port. And we can also verify this from the Istio system services section. And if you go all the way down, you will find ingress gateway. And within ingress gateway, if you look at the ports, you'll actually notice that the port 80 is pointed to the node port that we have just used. So you can also use the command line. That's actually better. So if you do if you do the get service on Istio system, you will actually find the ingress gateway, and in ingress gateway, internal port 80 is exposed as 31380. That is what we are basically grabbing in our URI. So now I'm going to open this in the browser, and keeping my fingers crossed, there we go. So this is the sample application homepage called product page. So currently everything is routed to V1, so you don't see any graphics related rating, for example, a red star or a black star, but the rating service is still called. You only get back the textual output, and this is the details microservice, and this is coming from the ratings and reviews microservice. So this home page in itself is a highly composable microservices application. So this comes from one service, this comes from the other, and this is actually a part of your static product page. Excellent. So far so good. Now what we'll actually do is to implement routing. Now the very first thing that I want to do is to apply a traffic rule that says whenever a user called JSON is logged in, he will see V2 of the review component, review microservice. So we'll actually implement that rule. So I'm going to roll out this policy that says, this is the rule, and every time it matches, send the request to V2 of reviews. And that is what we are going to deploy. And if you're curious to understand what goes behind the scenes, let's take a look at the YAML definition. So this virtual service says target reviews endpoint, but when the end user matches JSON, send it to V2, and if it doesn't match, send it to V1. That's exactly what we have told Istio via the pilot, and pilot pushes this to mixer, and mixer pushes this to all the envoy proxies. So now let's come back to the portal and sign in with username JSON, password JSON. And interestingly, this is going to show us V2 with all the black stars. Now, as long as JSON is logged in, he will only see V2 of the review component. This is fantastic. We didn't touch the code, we didn't do anything. This is running in production, and we rolled out a rule, a policy that said if the logged in user is JSON, show him a 5-star review based on black stars. Now, when I sign out, I can never see that anymore. That's because we have a very strong policy that is defined, as we have seen earlier, that is responsible for sending the traffic based on the username, which is injected into the header. Now, I can also roll out, for example, the combination of V2 and V3. So let's actually do this first. So now we are implementing a round robin mechanism of showing V2 and V3. So that means every time you refresh, you would see either black stars or red stars. So I have now deployed this rule, and I have signed out as JSON. And now the interesting thing is, when you actually refresh, it is going to show us, it's going to take, oops. Okay, I always face this. It's with the screen resolution. Give me a second, I'll fix this. Awesome. So, so every time we refresh, it's going to show us, one of the requests going to V2 and some going to V3. There we go. Now it became active. The rule is now applied. So randomly, when you start refreshing this page, occasionally you will see red, occasionally you will see black. And that is how we actually implemented this rule, which is the 50-50 split between V2 and V3. So let's take a look at the YAML definition for this. Pretty straightforward. Virtual service is reviews, route the traffic to reviews, but reviews has V2 and V3, and split the traffic across these two on a 50% ratio. So 50% of traffic goes to V2, 50% goes to V3. That's exactly what we rolled out. Now let's actually stabilize this entire traffic on V3. So now I'm rolling out a new policy that says send 100% traffic to V3, reviews V3. And now every time I refresh, I'll only end up seeing red. It's going to take a while to stabilize, but once it does, and after that you can never see black. All the traffic gets routed to red, which is representing the V3 of our component. And there we go. So now, I should have put this in an auto refresh, but if you actually see, there we go. So now every refresh only shows us red, which is an indicator that it is coming from V3 of the reviews component. Fantastic. So that's how simple it is to configure rules and policies for traffic management within Istio. Now, before I go any further, what I'm going to do is to roll out, again, V1, because that's the most stable, and it also gives us a consistent view. So I'm going to configure V1 for all, and now when I actually do a refresh, we'll not see any stars, but it falls back, it goes back to V1. Fantastic. Okay, now we are done with the traffic management concepts of Istio, and it's time for us to take a look at telemetry. So before we look at the telemetry dashboards, the visualization dashboards, what I want to do is to generate some traffic. So I'm going to run this in loop. So we're going to send some traffic to our microservice. So first we'll export the ingress host, the port, and then we are constantly hitting product page every 2 seconds. So this is going to generate some traffic. Let's keep this in the background. And now let's visualize the telemetry. By the way, Istio out of the box comes with Prometheus. Prometheus is an open source logging engine. It is very popular among the cloud native community. So it is already a part of Istio deployment. Similarly, Grafana, the visualization dashboard, the front end is also a part of Istio deployment. So when you actually look at the Istio system namespace and look at the services, you automatically see Prometheus and Grafana. So now let's go ahead and launch Grafana. So what we'll actually do is get the pod responsible for running Grafana from Istio system namespace. So we are filtering on label called app is Grafana, and we are grabbing the port and exposing that on 3000. So let's run this in the background. So now we have Grafana exposed. So let me go ahead and open the service dashboard. So this is going to show us a very powerful, beautiful dashboard. There we go. So this is the Istio service dashboard. It shows how many operations per second, what is the success rate. If there are errors, it actually shows up here, but because we don't have any errors, everything is a straight line. The success rate is 100%, which is fantastic. So obviously, I don't have enough time to drill down into every metric and every visualization, but as you can see, without writing any extra code or doing anything specific to our microservice deployment, we are able to visualize the health and insights from our deployment. So you can also access all the services. For example, here you notice that all the services that are registered are available here. So you can go all the way from the ingress to the product page, and now this gives you an insight into the product page. And if you want, you can go into reviews and also see how the reviews component is called. So this is the response code and the error rate. So a lot of details come from this, and it is very, very powerful. And all of this without ever writing a single line of code or doing anything specific to your application. So that is Grafana. I strongly encourage you to spend some time playing around with the dashboards and understand what these metrics mean. And tomorrow when you implement this for your own projects, this is going to be a treasure trove. So it's a gold mine. You can actually get a lot of very, very powerful, insightful information just from this dashboard. But that's not all. Let's also look at the tracing information. So there is another service called Jaeger that runs as a part of the Istio system namespace. And what we are now going to do is expose Jaeger. And Jaeger is an open tracing tool. It's a distributed tracing tool. And again, an open source project, integrates pretty well with Kubernetes and Istio. So we're going to run this and then access the Jaeger homepage from port 16686. So this is going to open another interesting dashboard. And this is again very powerful, but this is complementing the Grafana dashboard that we have just seen. So we'll go ahead and select one of the services, for example, product page, since that's the front end. Click on find traces, and there we go. So now it shows pretty useful information. And this is all about the spans and the tracing information. You can visualize the call chain and find out how long it takes for one component to call the other component. So this is the duration of the service invocation and how long it took for the request to come in and the response to go back. So you can actually click on any of these spans and it shows us very interesting data. For example, at the top level, we have the ingress gateway. That means typically every request is taking about 184 milliseconds, but that's not all. You can now drill down and figure out from ingress, how long does it take to reach the product page. And looks like, it is taking roughly 100 milliseconds. And after it reaches product page, it is calling details. And this round trip is taking about 4 milliseconds. And product page, when it is calling reviews, is taking 66 milliseconds. And for the reviews to come back, it is taking 6 milliseconds. So you can basically visualize the call chain in a very interactive form. And this again gives tremendous visibility into your call chain and your complete stack to understand how the traffic is flowing and how long it takes for one component to call the other. If there is a rogue service that is taking much longer than what is expected, it obviously becomes very visible here, and you can go ahead and fix that. So this also gives you a lot of opportunity to optimize your deployments and make sure that you can minimize the time it takes for the call chain to execute. So this is Jaeger, again very powerful out of the box with Istio. Fantastic. Now, one final thing that I'm very excited about showing you is a service called WaveScope from this interesting startup called Weaveworks. So we are now going ahead and deploying that into our cluster. So let me put this in watch mode. So watch kubectl get pods from a namespace called Weave. So currently there is nothing. We are going ahead and deploying WaveScope. It's an app that will help us visualize our services architecture. So it should just take a few seconds for the pods to show up. And as soon as that is done, we'll go ahead and access the WaveScope app. So there we go, 12 seconds, not bad at all. So now I'm going to grab the pod responsible for WaveScope app, and then we'll expose that on port 4040 as the node port, and then we will get the actual node port and open the WaveScope app from the ingress and the node port. Perfect. So now this shows up, and WaveScope is a fairly interesting, powerful application. Integrates pretty well with Kubernetes and the microservices app. So now it is processing topologies, and it has cluster-wide access because it is actually deploying as a daemon site. It has visibility into the entire cluster, not just a namespace or an app. So very soon we'll actually see all the namespaces showing up here. It shouldn't take so long. Maybe it's initializing. Let's give it a few seconds. And once the namespaces show up, we'll click on default, and there we're going to have a surprise. It actually shows the entire topology in a very eye-appealing, eye-pleasing graphic. Okay, few more seconds and this should be fine. Let me check if there are any errors in the pods. No, there are no errors, there are no restarts. So I think it is initializing. Behind the scenes, it does some plumbing, and there we go. So now if you actually see, all the namespaces are showing up here, and it is still doing some housekeeping. It is verifying the pods. Now let me click on default. Now when I click on default and when it is done with the plumbing and the initialization, we should actually see a topology which is pretty interesting. So it normally doesn't take so long, but let's see. There we go. So now we have the controllers. Controllers are basically the replica sets or deployments. So now if you actually see, this has a very nice, let me refresh to make sure. Okay, I'm going to relaunch the portal with the default. Oops. Okay, looks like something went wrong. My WaveScope pods are no more running, so that's the reason why we couldn't access. So let me see what actually went wrong. So okay, my Minikube is up and running. Okay, so now it has come back. Now looks like there was some disconnect somewhere. So let me go ahead and expose the okay, so let me first expose the pod. Okay, I need to get rid of this. So kubectl delete service namespace is wave, and the service name is WaveScope. I want to do this all over again to make sure it is wiring up to the right pod. So let's first grab the pod and then expose it. and then we'll actually do a port forward. Okay, so now we will actually open Wavescope all over again. This is pretty resource intensive. I'm actually running the whole of Istio and a microservices application along with third-party applications like Wavescope. And of course, don't forget the Grafana, Jagger, and other like Kiali and other stuff that I already have in the system. So now I'm going to click on default namespace, and there we go. This is exactly what I wanted to show. So now you can actually see how the topology is available to us. So there is product page that calls, ratings v1, details v1, and reviews v1, v2, and v3. So it is pretty interesting to see how this is laid out. You can also look at the number of pods and how they are basically connected. So within each pod, you also have the number of containers that are actually being shown, and you can also see the details about each of the containers. And the best thing is you can also actually get to access the terminal logs. So currently it is showing us the entire log coming from both the containers, the Envoy proxy and the ratings container. So pretty cool. And you can not only use this, you can also actually scale the number of instances. So you hit the plus button, you can actually increase the number of replica sets. Very cool, very powerful way of dealing with your microservices deployment. So that is about Wavescope. We are almost at the end of this demo, and I'm spot on time. It's been 60 minutes since I started. Fantastic. So that brings us to the end of this Istio demo, everything that you wanted to know about Istio. So we have gone from installing Istio to configuring traffic rules to visualizing insightful telemetry, all of that in one session. And in one of my upcoming sessions, I promise to bring you a focused session on security, MTLS, and authorization. So that deserves a session for itself. So stay tuned for that. I'm going to announce it maybe next quarter. So summary: automatic load balancing provided by Istio, fine-grained control of traffic behavior. Remember how we could route traffic from V1 to V2 to V3, all with one command, kubectl apply. Pluggable policy layer and configuration API to configure access controls, rate limits, and quotas. Automatic metrics, fantastic and powerful visualizations. And secure service-to-service communication with an MTLS authentication and authorization. So that was a quick summary of what Istio does to your microservices deployment. So I want to thank our sponsors, the New Stack, our media partner. This entire session is documented as a tutorial, and it's going to show up on New Stack. The link would be on YouTube video. Just click on more and you will find the link to the New Stack article. Foghorn, a Bay Area based edge computing company doing pretty interesting stuff. It's a multi-cloud edge computing company. Portworx, one of the pioneers and leaders in container native and cloud native storage. They are helping enterprises productionize microservices by running stateful workloads on par with stateless workloads. Now, I want to announce the next session, running applications at the edge with AWS Greengrass. This is going to be on May 16th, right after I come back from Microsoft Build. I'm going to be in Seattle attending and participating in Microsoft Build. So as soon as I come back, I'm going to prepare and deliver this session on AWS Greengrass. Like all of my sessions, this is going to be a live demo. I'm going to pick up a system on chip computer and then install Greengrass and run a Lambda function and show some interesting use cases. So register at mi2.live. Thank you so much for attending this webinar. And if you're watching this on YouTube, don't forget to click on the subscribe button and click on the bell icon for notifications. I am committed to bring you high quality, cutting edge content. Thank you. This is Janakiram signing off.